Completely by accident, in the last few weeks, two separate teams from two separate universities released somewhat intriguing research on the idea of Snowball Earth, the unusual period in the history of our planet when the entire planet was basically covered in ice. The event that happened several times, with one of the last ones and one of the more interesting ones happening approximately 650 million years ago, the period known as Cryogenian, and a period that was actually very likely in two parts, as in the first Snowball Earth finished and then the next one started not so long afterwards. And so because of these very unusual and very extreme Ice Age related events, the researchers have always been trying to figure out exactly what happened and what might have caused our planet to become basically a snowball. And so we have these two separate papers that focus on slightly different things and do make some really intriguing discoveries. Although I guess a quick side note, a lot of these are actually based on simulations and not actual evidence, and so there's still a bit of uncertainty. But anyway, one of the more important reasons why the scientists actually want to study this is to understand how our planet naturally maintains the overall climate balance and how it tends to recover from some of the more extreme events. Somehow planet Earth has been able to maintain relatively similar temperatures for billions of years, and that's of course one of the bigger mysteries. And pretty much every study to date continuously confirmed that a lot of this regulation seems to be done through carbon dioxide. And so it's actually the CO2 concentration and how it's recirculated in the air that seems to drive most of this. Now things like methane and a lot of greenhouse gases also obviously add quite a lot of heat or remove heat, but in this case they do not provide a long-term stability, but CO2 does. And so in one of the recent studies, researchers decided to focus on various models involving plate tectonics and the connection between that and of course CO2. And so first of all, we know for a fact, based on a lot of different studies and a lot of different geological discoveries, that in between 717 and 660 million years ago, our planet was very likely what you see right here. And what's super unusual about this is that it might have lasted for 57 million years. And that's of course a very unusually long period for our planet. Now during this time there were obviously no animals, no trees, nothing on the surface, but the oceans were filled with life, and a lot of it was multicellular and complex. And so somehow life survived this so-called Sturtian glaciation. Probably one of the more mysterious, but also potentially one of the more important events in the Earth's history. And so here, by using the continental plate modeling, the researchers were able to show the evolution of continents that followed the breakup of an ancient supercontinent, Rodinia. A continent that we believe might have resembled something like this. And a continent that started to break apart 750 million years ago, which lasted for 120 million years. Although in this case it was also connected to modeling involving CO2, and specifically the models involving CO2 degassing that happens in underwater volcanoes along various continental plates. And what they've discovered is that there is a really high correlation between extremely low CO2 levels, very likely caused by degassing due to low volcanism, and the ice age that lasted for 57 million years. In other words, it looks like there's a really strong correlation between low CO2 during this time and our planet being this. But in this case, the low CO2 levels were caused by previously deposited volcanic rocks that over time ended up absorbing a lot of the CO2, which possibly took approximately 2 to 3 million years. But it's really because of the plate tectonic reorganization, which was a result of Rodinia breaking up, that's actually caused volcanism to decrease dramatically and a lot of CO2 on the planet to suddenly become consumed by various volcanic rocks that were deposited previously. And so here it was discovered that the levels of CO2 were possibly 200 parts per million or even less, which is basically half of the levels we have today. But more importantly, this lasted for 57 million years. And mostly because, well, on the surface there was really nothing else to influence CO2, and it's actually the volcanoes and the gassing by rocks that were mostly responsible for changing the levels of various gases in the atmosphere. During this time, a lot of marine life was just not as influential as it is today. And I guess to some extent this is an intriguing discovery, because based on geological research, scientists currently believe that Earth may actually experience lower volcanic CO2 emissions in the next few millions of years, mostly due to additional continental collisions and a much lower activity from continental plates. And at some point in the next 200 million years, we might actually see another supercontinent, which we've discussed in one of the videos in the description. And so the question is the Earth going to become a snowball once again? Well, we still don't know, but previous studies suggested otherwise. Actually, some of the previous studies even suggested that in approximately 200 million years from now, Earth might actually become way too hot instead, causing a lot of life to kind of disappear. And so in that sense, there is still no way to predict exactly what's going to happen. But one question that's not really answered in this study, and one question that is important, is of course the idea of what triggers these events. We know our planet went through a lot of different changes in billions of years, but these changes did not always result in a snowball Earth, even though they should have. And so that's where that second study comes in and potentially provides a somewhat important answer. A physical trigger that usually causes the planet to go through some extreme changes that last for millions of years. And as you might have guessed already, it more or less seems to be this. Okay, so not exactly as extreme as this, but basically it is potentially major collisions. And once again, this new study decided to use various simulations and modeling to try to figure out what would essentially happen to our planet if an asteroid crashed on a surface during several different periods of history, periods when Earth was warmer or colder. Would it cause some kind of a runaway effect that would then transform the planet for millions of years? And while previous research always tried to explain snowball Earth as a result of a runaway effect based on the snow and ice reflectivity. Or basically, the colder the planet gets, the more ice it gets, the more light it starts reflecting, which then results in even more cold. A kind of a cycle that continues until the planet becomes a snowball. Now that was an interesting explanation, but there was obviously no evidence. Here though, the researchers used a really advanced simulation and modeling technique, the technique referred to as Ocean General Circulation Model, in order to simulate a potential asteroid strike during pre-industrial era, last glacial maximum 20,000 years ago, Cretaceous period 145 million years ago, and Neoproterozoic, which was approximately 542 million years ago when the Earth was colder. And turns out that during the warmer periods, which is of course the modern period, pre-industrial period, and the Cretaceous periods when the dinosaurs were around, any kind of an asteroid collision would not cause a global glaciation because the planet would recover from all of this within a few 100,000 years. But for much colder periods, in this case last glacial maximum 20,000 years ago, and the period 600 million years ago, an asteroid strike could potentially trigger a snowball Earth. And this would only take approximately 10 to 20 years maximum. In other words, the actual feedback mechanism would be very effective and cause the planet to freeze for many years. Which is of course a somewhat intriguing additional study that explains why even during certain periods when Earth could have become a snowball Earth, it didn't. It probably just did not receive powerful enough collisions to cause all of this to happen. But this of course also implies that the two major glaciation periods that lasted for millions of years might have also started or have been triggered by some kind of a collision that we don't really know much about. For example, we know that at least two major impacts, actually some of the biggest on Earth, the Beaverhead impact and the Ackermann impact, happened around that time, and so they might have had some effect on causing the planet to become cold. But that's just a speculation, and once again there's just no evidence. Nevertheless, very intriguing studies and very interesting discoveries in regards to climate regulation on planet Earth, and of course a few more explanations for why our planet sometimes reaches some really cold temperatures. But we still have a lot more mysteries, including the mystery of some really hot periods, that we're going to discuss in some of the future videos, and you can actually learn more about in one of the videos in the description. For example, there's an unusually hot period, approximately 54 million years ago, that we still cannot explain very well. Anyway, once we learn more, and once there are additional discoveries, we'll come back and talk more about the snowball Earth a little bit more. Until then, thank you for watching, subscribe, share this with someone who loves learning about space and sciences, come back tomorrow to learn something else, support the channel on Patreon by joining channel membership or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.